How mass, density, and volume affect gravitational force. The equation for density is ρ equals mass over volume. Density is ρ, here's your mass, and here's volume. The volume of a sphere is 4/3 pi r cubed, where r is the radius of the sphere. Now we can see what happens to the gravitational force between two objects when the mass, density, or volume of one or both objects is changed. Examine the gravitational force between two spheres. Since ρ is mass over volume, mass is just ρ times volume. Therefore, Newton's law of gravitation becomes this. We just replace the masses with ρ times volume. Since the objects are both spheres, we use this volume formula, and we'll label each sphere with its given radius r1 and r2. So this equation here, which we have from the previous slide, we replace volume, in each case, with this factor here. In the denominator, the distance between the centers of the objects is r1 plus r2. Right? The distance between the objects are 0, but that's not what we put in the equation. We have to go to the center of mass of both objects. This is not an equation that you should memorize. You should be able to derive it if needed using ρ equals mass over volume and the volume of a sphere, both on the AP Physics 1 equation sheet. Let's go through an example problem where this equation will be used. There are two planets, planet X and planet Y. They have a gravitational force of F sub g between them. What will happen to F sub g if the radius of planet X were to be doubled? The distance r between the planet's center of masses remains the same. So this term right here stays the same. So even though this one gets bigger, just kind of draw a partial circle, we don't worry about that. We just have to calculate between the two centers of mass. We use something called the factor of change method. Put a 1 for any variable or constant that does not change. Put the factor of change for any variable or constant that does change. So here's our equation. The only thing that is changing is r sub x. Since it is doubling, we put a 2. Everything else gets replaced by a 1. So we label the constants 1 and also any variables that are not changing. And the only thing that's changing is r sub x. We've doubled it, so there's a 2 there. So this is from the previous slide, the factor of change. The 2 is to the third power, so there's cubed. 2 cubed is 8. So now we have an 8 there. We simplify that fraction, and we get the factor of change is equal to 8. Therefore, by doubling the radius of one of the planets, but keeping the mass and density constant, the force of gravity between the planets increases by a factor of 8. Using the factor of change method will come in handy all throughout this course. Rewrite the equation for surface gravity in terms of density and radius. We're going to set the radius equal to the radius of our planet because we're looking for the value of g on the surface. So here's our expression for g, the gravitational acceleration. We substitute this in. That's going to be what? That's the mass, right? It's ρ times volume. And we simplify it to get this answer right here. A non-rotating perfect sphere of uniform mass density, or whose density varies solely with distance from the center, which is spherical symmetry, produces a gravitational field of uniform magnitude at all points on its surface. The Earth is rotating, however, and it is not spherically symmetric. Rather, it is slightly flatter at the poles while bulging at the equator. There are consequently slight deviations in the magnitude of the gravitational acceleration, of course, which is g, across its surface. It varies from 9.863 meters per second squared at the North Pole to 9.798 meters per second squared at the equator.